In this video, we're going to continue our discussion of work integrals. We're going to look at Hooke's law. The force f of x required to stretch a spring x units beyond its natural length, beyond its equilibrium length, is given by f of x is equal to kx, where x is a stretch beyond equilibrium or equivalently is a stretch beyond its natural length, and k is the spring constant. So in the first instance, we have an equilibrium. We have an equilibrium. The reason for that is that x is equal to 0. X is a stretch beyond the equilibrium, and this spring has been stretched 0 meters from equilibrium. The force is 0. Force is equal to 0. In the second case, the spring is stretched. It's stretched because x, which is the length of the spring that's been stretched beyond equilibrium, and x is positive in this direction. And the force is also positive. Notice that the force and the displacement are always in the same direction. And this is always the case, even when the spring is compressed. So in the third case, we have a compression. The spring is compressed. X is negative. X is less than 0. The force is also negative. So x is compressed this distance. And the force is negative, and work, of course, is force times distance. So when you integrate, you're always going to get a positive quantity for the work. And that's why we're going through these. All right. So we have the diagram here. We have f of x is equal to the force function is kx. That's Hooke's law. X is positive. And we have a stretched spring. Stretched. Now, in the third quadrant, x is negative, and we have a compressed spring. Let me say that properly. Compressed spring. All right. Okay, so the work done is simply the area under the curve from x equals a to x equals b, because the force is being applied from x equals a to x equals b. So work is equal to integral from a to b f of x dx. But the force function is just kx according to Hooke's law. So work is integral a to b kx dx. So the integration for all of these spring questions is going to be really easy. It's really just the basic idea of wrapping your head around the physics aspect of it. All right, so let's look at an example. Here we have a force of 20 newtons is required to stretch a spring 10 centimeters from its equilibrium position. Find the spring constant K. Part B, how much work is required to stretch the spring 20 centimeters from its equilibrium position? Part C, how much work is required to compress the spring 10 centimeters from its equilibrium position? Part D, compute the extra work needed to stretch the spring an additional 15 centimeters when it has already been stretched 5 centimeters beyond its natural length, beyond equilibrium. All right, we're going to do those one by one. For the first part of the question, find the spring constant K. According to Hooke's law, f of x is equal to kx. And we're stretching the spring 10 centimeters. That's 0.1 meters. We have to use the units of meters. So f of 0.1 is equal to k times 0.1, and the force is 20 newtons. The force needed to stretch the spring 10 centimeters beyond equilibrium is 20 newtons. If we solve for k, we get k is equal to 20 divided by 0.1, and that gives us 200 newtons per meter. What that means is that it takes 200 newtons of force to stretch the spring 1 meter beyond equilibrium. This is the spring constant. Now let's look at part B. Find the work needed to stretch the spring 20 centimeters from its equilibrium position. Equilibrium position, of course, means x equals 0. All right, so we want to stretch the spring 20 centimeters from x equals 0 to x equals 0.20 meters. We have to use the metric system, of course, so we change 20 centimeters to 0.2 meters. Work is integral from a to b f of x dx. This is equal to integral from 0 to 0.2, 200x, because we already solved for k. This is a force function according to Hooke's law. This is kx dx. Now applying the reverse of the power rule, we get 200 x squared divided by 2. Add 1 to the exponent, divide by the same, evaluate from 0 to 0.2. And we get, applying fundamental theorem of calculus, 200 divided by 2, that's 100. Put the upper limit in, we get 100 times 0.2 squared minus 100 times 0 squared. So the result is 4 joules if we simplify this. That means 4 joules of work are needed to stretch the spring 20 centimeters from its equilibrium position. All right, let's look at part C. Find the work needed to compress the spring. So we're compressing the spring 10 centimeters from its equilibrium position. Since we're compressing the spring, we have to integrate the force function f of x from x equals 0 to x equals negative 0.1. Key concept is a negative displacement. X is negative 0.1 centimeters. So the work is the integral from 0 to minus 0.1 kx dx, that's 200x dx, that's our force function. According to Hooke's law, this is kx. And we integrate using the reversal power rule, we get 200 x squared divided by 2, evaluated from 0 to negative 0.1, applying fundamental theorem of calculus. We're going to get 100 times negative 0.1 squared minus 100 times 0 squared. If we simplify this, we get 1 joule. That means 1 joule of work is required to compress this spring 10 centimeters from its equilibrium position. All right, so now let's look at part D. Part D is asking us to find the extra work needed to stretch the spring an additional 15 centimeters when this spring has already been stretched 5 centimeters beyond equilibrium. Now, it's very easy to make a mistake here because we have to realize that we're stretching the spring an additional 15 centimeters. So that means the total length of the spring beyond equilibrium would be 15 centimeters plus 5 centimeters, which is equal to 20 centimeters. So we have to be very careful with this. So we have to integrate from x equals 0.05 meters. This is a stretch beyond equilibrium, 5 centimeters stretch beyond equilibrium. And we're finding the extra force needed to stretch the spring additional 15 centimeters beyond the 5 centimeters that already has been stretched. So the new x is equal to 20 centimeters. Changing that into meters, that's 0.20 meters. So applying the work function, work is equal to integral from a to b, f of x dx. And a is equal to the lower limit of integration. Lower x value is 0.05. Upper x value is 0.2. Kx dx, that's 200x. This is kx. And we integrate this, we get 200 x squared over 2, reversing the power rule. Applying the fundamental theorem of calculus. Put the upper limit in and the lower limit in and evaluate. So the work is 100 times 0.2 squared minus 100 times 0.05 squared. If we simplify this, the work is going to be equal to 4 minus 0.25 is equal to 3.75 joules. This means that 3.75 joules of work are needed to stretch the spring an additional 15 centimeters when the spring has already been stretched 5 centimeters. This is a very typical exam question, so make sure that you do this correctly. All right, thank you.